Hello everyone, this is a lecture again on igneous petrology. We are covering basically the course for GSI, and this is a lecture number 9 in YouTube. And here in this lecture we will start the classification of igneous rocks. Okay, so let's start with classification of igneous rocks. So first thing is the types of magma. Okay, how many types of magmas are there? We have basaltic magma, zoom a bit. We have andesitic magma and we have rhyolitic magma. So in basaltic magma, the SiO2 percentage is from 45 to 55%. Basaltic magma is rich in Fe, Mg and Ca, and they have low potassium and sodium. Okay, and the temperature is also high for basaltic magma. Now andesitic magma have 55 to 65% of SiO2. They have intermediate Fe, Mg, Ca, Na and K, and the temperature of this is also intermediate. Now if we see the rhyolitic magma, the SiO2 percentage has been increased to 65 to 75%. It has low Fe, Mg and Ca, and they have high Kn and Na. They have high potassium and sodium. Okay, so if you see from basaltic magma to rhyolitic magma, what is increasing? Our SiO2 concentration is increasing. Our SiO2 percent is increasing. Okay, SiO2 percent is increasing. As SiO2 percent is increasing, so viscosity also increases from basaltic to rhyolitic magma. So here SiO2 percentage is 45 to 55%, and here SiO2 percentage is 65 to 75%. Now if we see the gases in magma, so when the magma is at a certain depth where the pressure is very high, these gases are dissolved in the magma, and when this magma erupts through the volcanoes or volcanic vent, the pressure in the atmosphere is less as compared to pressure underneath. So because there is a less pressure, these gases which are dissolved in the magma will no longer able to get dissolved. Okay, so just like our cold drink bottle is there, when we open the cap of a cold drink bottle, the CO2 gas start to come out, which is because of the decrease in pressure. Similarly, when the magma erupt and changes in the lava, the gases which were dissolved in the magma will no longer able to get dissolved, and they will convert into vapor phase and get out of the magma. So if you see here, at the depth in the earth, nearly all the magma contained dissolved in the liquid, but the gases forms a separate vapor phase when the pressure is decreased as the magma rises towards the surface. Okay, it is similar to the carbonate beverage at high pressure. The high pressure, the high pressure keeps the gas in the solution, but when the pressure is decreased, like when you open a can or a bottle, the gas comes out of the solution and forms a separate gas phase that you see as a bubble. Just like our cold drink bottle, same phenomena is happening here. Okay. Now these gases in the magma, they give explosive characters to the volcano. If the more gases are dissolved in the magma, it will become more explosive when coming out of the vent. Okay, and after that we will see the composition of gases. It is mostly it is H2O. Okay, and some CO2 is also present. Minor amount of sulfur, chlorine and fluorine gas also is present. Now the amount of gases in the magma is also related to chemical composition of magma. For example, rhyolitic magma usually have high dissolved gases content than the basaltic magma. So if you see, if the rhyolitic rock is there, okay, or rhyolitic magma is there, so the volcano will be more eruptive. Okay, for example, our Pillenian and Palinian type of Palinian volcanoes. Okay, and if the source is our basalt, okay, if basalt is there, then if basalt is there, then it will be less eruptive. Okay, and which type of volcano you will get here? You will get shield type of volcano, shield volcanoes. An example is like Hawaii. Okay, Hawaii, Fauna Loa is there, no, Mount Fauna Loa, Mount Fauna Loa is there. So it will be a shield type of volcano, means if it will spread a lot, it will spread laterally a lot, and it will be less eruptive. Now if you see the temperature in magma, so basaltic magma have the highest temperature, it is around 1000 to 1200 degrees Celsius. Andesitic magma have an intermediate temperature from 800 to 1000, and rhyolitic magma have temperature around 650 to 100 degrees Celsius. So viscosity increases in this direction. Okay, viscosity increases in this direction, temperature increases in this direction, and SiO2 percentage increases in this direction. Now if we move toward the viscosity, okay, so as I have told, high SiO2 content will have a high viscosity and it will have a low temperature. Okay, this will be like this, and it will have a low temperature. And if we talk about the eruptive nature, so eruptive nature will also increases with increasing SiO2 content. Now if we see, the lower temperature magmas have higher viscosity like our rhyolitic magma than the higher temperature magma. So as the viscosity is your decreasing, SiO2 percentage is also decreasing, like we have seen in case of basaltic magmas. Now if we see further, more SiO2, more felsic magma and have more viscosity, less SiO2, mafic magma, less viscosity. Okay, so this we have already seen in detail. So we can, if we see here, the basaltic magma tend to be a fairly fluid, low viscosity, but their viscosity is still 10,000 to 1 lakh times more than water. Okay, it has less viscosity, that does not mean it will flow like a water. And if you see, this basaltic magma makes some kind of surface features also, like Pahoho is there, Pahoho is there. It is a superficial feature of basaltic lava. Okay, so in this, what happened, the lava start to flow and it solidify, a plastic skin type of thing develop on the top, and it is quite smooth, and you can see this in the Hawaiian region. So it will form a superficial feature which is known as pahuhu. Now rhyolitic magma tend to have higher viscosity, ranging between 1 million to 100 million times more viscous than the water, and here we will see AA as a superficial feature. Okay, it will be much more blocky rather than smooth. Okay, blocky, like brachiated or blocky type of feature you will see. Now viscosity is important in determining the behavior of the eruptive behavior of the magma. So this is a summary table of whatever we have studied. Okay, so let quickly go through it. If the magma type is basaltic, it will solidify to basalt. SiO2 concentration will be 45 to 55%, high in Fe, Mg, and low in Kna. Temperature will be 1000 to 1200. Viscosity will be around 10 to 10 to the power 3 pascals. Gas content is low. Andesitic magma, it will solidify to andesite. SiO2 percentage is between 55 to 65%. Intermediate amount of Fe, Mg, Ca, Na, K is present. Temperature is around 800 to 1000 degree, and viscosity, if you see, it is increasing. Now it is 10 to the power 3 to 10 to the power 5 pascal. Gas content is intermediate. If you see the rhyolitic magma, it will solidify to rhyolite. and SiO2 percentage is around 65 to 75 SiO2 percentage. It has low FeMgCa and high KNNA, and temperature is around 600 to 100 degrees Celsius, and viscosity is quite high here, which is around 10 to the power 5 to 10 to the power 9 Pascal, and it has high amount of dissolved gases like H2O, CO2. Okay. Now, if you see the classification of igneous rocks here, so first we will study about the pheneritic igneous rocks. Okay, pheneritic igneous rock. Now, if we see the pheneritic igneous rock, they are coarse grained rocks. Okay, pheneritic means they have phenocrest and a ground mass. So, phenocrest are basically big in size, and ground mass will be smaller in size. So, these pheneritic igneous rocks, if we see here, we have quartz, here we have alkali feldspar, and here we have plagioclase feldspar. Okay, now for exam point of view, you just have to memorize this entire table, whole table. So if we see this line here, this one, here 90% quartz is there, here 60% quartz is there, here 20%, and here 10% quartz is there. So 10% quartz line is this one. Okay, now if you see this percentage here, 90% if quartz is present, okay, then it is known as quartzolite. And in this diagram here, in this side, this portion, this one, this is a boundary where no alkali feldspar is present. Here your plagioclase feldspar is there. Okay, this is diorite, gabbro, and anorthosite, both are plotted here only. Okay, now in the this end of this triangle, here we have a feldspathoid. So one question has been asked in GSI, explain about feldspathoid. So you can draw this below triangle, which is from here. I'm drawing with black color. This one is our feldspathoid. Okay, so here 60% feldspathoid is there, and here 20% feldspathoid will be there. Okay, now if you see the rocks which are forming here, you have a tonalite. Okay, tonalite have high amount of plagioclase feldspar. Here we have a granite. Okay, granite has an intermediate composition of alkali feldspar and plagioclase. It has also quartz. Okay, 60 to 20% quartz is there. Here we have granodiorite. This is a boundary for alkali feldspar granite. In between here it's quartz and rich granotite. Here we have cyanite, monzonite, monzodiorite. Here we have quartzite, quartz monzonite, and quartz monzodiorite. And below will be simple because it's void now. Okay, void means it lacks silica percentage. Okay, silica percentage, it does not have silica percent in it. So if you see here we have void bearing cyanite, void bearing monzonite, void bearing monzodiorite. Here we will have void gabbro, here monzodiorite, monzocyanite, and here void cyanite will be there. So here I have written the above figure represent the classification of pheneritic igneous rocks, pheneritic rocks with more than 10% quartz feldspar plus feldspatite. Okay. Now this question is classification of gabbroic rock. So you can remember with the term PPO. Okay, PPO means from this order P, P, O. So it will be plagioclase. Here will be pyroxene, and here will be olivine. Now here, if you see, this is the 90% plagioclase line. Here will be 10% here. Okay, this rock is known as gabbro, which has plagioclase and pyroxene. Here we have troctolite. Don't get confused with tonalite. In tonalite is present here where it has quartz and plagioclase feldspar. And this here, this one, this zone, it is known as plagioclase bearing ultramafic rock. This is plagioclase bearing ultramafic rock, and in between you have olivine gabbro. Okay, and here when 90% of the plagioclase is present, it is known as anorthosite. It is known as anorthosite. Okay. Now classification of ultramafic rock. This is very important question. for GATE and GSI. So here you can see, you can first you have remembered PPO. Here you can remember OOC. Okay, so PPO was looking like this. Okay, and OOC, here will be your olivine, here will be your OPX, and here will be your CPX. So if we dwell more into detail in this one, so we can see here that here is olivine, and if a rock contain 90% of the olivine, it is known as dunite. Here in the 40% we will draw one line. Here will be a larzolite. It has intermediate composition of orthopyroxene and chlorpyrrocene, along with it has olivine in it. Okay. Now this line 10% here, the rock is orthopyroxenite, and same in the clinopyroxene. Here the rock will be clinopyroxenite. Okay. And here will be our olivine webstrite, and here is larzolite. And the rock which contain olivine and orthopyroxene is known as harbourgite, and the rock which contain olivine and clinopyroxene is known as weyerlite, and the rock which contain orthopyroxene and clinopyroxene is known as webstrite. So here olivine webstrite will come, which contain clinopyroxene, orthopyroxene also in higher quantity, and it contain less than 40% of the olivine, and the intermediate composition will be your larzolite. Okay, and I have drawn one line here, if you can see, from 40% this, whatever rock is below it is known as pyroxenite, and whatever rock above it is known as peridotite. Okay, now if we see the classification of aphanetic rock, which are fine grained and also known as volcanic rock, same thing is there. Here is the 60% mark is there. Here we get rhyolite, which is volcanic equivalent of granite. Here we will get dacite, which is volcanic equivalent of granodiorite, and you can compare both the figures to see the different volcanic equivalent. Here we have trachyte, which is volcanic equivalent of cyanide. Here we have latite, which is volcanic equivalent of monzonite. Okay, and what else we see? Yeah. And here we have andesite, which is volcanic equivalent of monzodiorite. And here we have phonolite, here we have tephrite, and here we have phodites. So phonolite is a volcanic equivalent of monzocyanite. Phonolite is a volcanic equivalent of monzocyanite, and tephrite is volcanic equivalent of monzodiorite. Okay, so this is the classification for a phenetic igneous rock. Now if we see the TAS diagram, okay, that is total alkali silica diagram. In y-axis we plot weight percentage of Na2O plus K2O, and in x-axis we have weight percentage of SiO2. Now if we how to draw this diagram, first we will make this line, okay, then we'll make this line, and then we project it like this. Okay, whatever I'm highlighting, this is trick to draw this diagram. Okay, now what you do, you make another line from here like this, and make another line like this. Now you can make a subdivision like this. From here you start and take this line above, make a triangle, and again take this line above. Similarly, make one more division here, take here, and then again take it here. Similarly here also. Okay, this is a simple way to draw this diagram. Now if we see, here we have picrobasalt, okay, which has less silica in it. Then we go to basalt, then basaltic andesite, then then dacite, and the high percentage you will get in rhyolite. Okay, so if the percentage of Na2 and K2 increases, you can see here you will get trachybasalt, then basalt trachyandesite, then trachyandesite, then trachyte. Okay, similarly here we will get picrobasalt, then tephrite, then phonotephrite, then tephri-phonolite, and then at the end you will get phonolite. Now phonolite has the highest percentage of Na2O and K2. Now if we draw a line passing through origin in this one like this, okay, so whatever a rock which is above this line, this one, these all are alkaline rocks, and whatever rocks which are coming below are known as subalkaline rocks, and these all are intermediate, okay, because it is in the same zone. This picrobasalt, basalt, basaltic, andesite, they are subalkaline rocks. Tephrite, phonotephrite, tephri-phonolite, and phonolite are alkaline rocks. Now, if we see the classification of pyroclastic rocks, so pyroclastic rocks are the rocks which comes to the volcanic vent, okay, which comes outside to the volcanic vent. So here, if we see, here we have blocks and bombs, okay. Now, what is different between blocks and bombs is your blocks is formed from dead lava, okay. It is already solid in nature when it is coming out from the volcanic vent, and it is highly angular in shape. And the bomb is, it is in liquid state, and when the lava is ejected in the atmosphere, so before falling to the surface, if that lava gets solidified, it will be a very smooth kind of surface it will be, and that will be a bomb, okay. Size, if you see, it is size will be greater than 2 mm. Now, a combination of block and bomb is known as agglomerates. So if anyone has more than 75 percentage of blocks and bomb, we call it agglomerate. Here we have lapilli, okay. Lapilli is small size, okay, granules. Size is 22 to 64 mm. And if you become much more smaller in size, we call it as ash, whose size is less than 2 mm, okay. In between that, we will get a tuff breccia. In between lapilli and ash, we get a lapilli tuff. If the rock is fully composed of lapillis, we call it as a lapilli stone. And if a rock is made only of ash, we call it as a tuff. So tuff is rock made from ash. Okay. Now, if we move to the alumina saturation, okay. So if we see, the feldspar have most common mineral which contain aluminium. Okay. Now if we see this one, this is anorthite. This one is albite, and this one is orthoclase. So if you see here, all of them have Al2O3 in their composition. Okay. Now if the Al2O3 percentage is greater than CaO, Na2O, and K2O, that type of rock is known as para-aluminous rock. For because para-aluminous rock, because this rock will be rich in Al2O3 rich minerals, for example muscovite and corundum. Okay. Meta-aluminous rock will be what? If your Al2O3 is less than CaO, Na2O, K2O, then we'll call it as meta-aluminous rock. But one thing you remember is, if you remove CaO from here, then the sign will change here. Okay. So this is important property of meta-aluminous rock, because they also have aluminium, but the sum of CaO, Na2O, K2O will be greater than Al2O3, but the sum of Na2O, K2O only will be less than Al2O3. So most common, they lack Al2O3 rich mineral, okay, lack of sodic pyroxene and amphibole. Now if we move to per-alkaline rock, per-alkaline rock is oversaturated with alkalis. So here Na2O, K2O will be greater than Al2O3. Now this we have seen in the TS diagram. The rocks which are above were all alkaline rocks, and the rocks which were below all are subalkaline rocks. So this completed our lecture number 9 on classification of igneous rocks uh, and the types of magma and all. In the next lecture, we will study with the textures of igneous rock. So thank you for watching, and keep supporting for more videos.